All right. Now, integration in kinematics. It's in here. Write the math contest in this room at lunch. You can. It's only half an hour long, and you can start at any time in the lunch hours. And once you start, you get half an hour from there. So we know that if we take the derivative of displacement, we get velocity, and if we take the derivative of velocity, we get acceleration, which can be easily remembered with the word SLA. But if you do the derivative to work this way, we can integrate and work backwards. And so we will do some problems. Some of these, for you physics people, you will be like, oh, I learned some physics formulas. The beautiful thing about calculus is it's like, if you understand calculus, you don't need formulas. You just figure it out. So we'll look at some questions like that. The acceleration of a particle moving in a straight line is given by t plus 1. Find the equation for the velocity and displacement, and they give you certain initial conditions. So our velocity, if we were working backwards from acceleration, would just be the integral. And if you integrated that rather easy integral, get t squared over 2 plus t plus c. But we know that at time 0, velocity is 8, so we could plug in 0 for t and 8 for our velocity, and we get c, so we get an equation for velocity as t squared over 2 plus t plus 8. So this is very similar to our differential equations earlier where we had to solve for the c. We're doing that again, but just in an application question of kinematics. So now if we want to find our displacement equation, we would have to integrate our velocity equation. And doing that, now be careful, because if you used a c here, we shouldn't use c again in the same question. Sometimes you'll see C1 and C. Sometimes people do C1 and C2. I usually like to use the letter D after C. But you can use anything that you like. In this case, I went with K because they have the same sound depending on the word. No. So, we have an initial condition. Again, we know that when time is 0, displacement is 0, so we can solve for K, and K is 0. So we have our displacement equation as well. Grab this. I'm going to let you try this next one on your own. All right, let's see how you did. So if you're going from velocity to acceleration, then you take the derivative. And if you want to go from velocity back to displacement, we have to integrate, and we have to solve for c, and you get a c value of -40. I mean positive 40, sorry. All good? Awesome. Not too bad, right? I usually find that some of the, like the basic velocity and acceleration, they don't give you really hard integrals to work with, so it tends to be almost an easier question. Because they're really seeing, do you understand the relationship between them? And they don't really give the hardest questions all the time. So again, here we're given acceleration. Again, I'd like you to try this one on your own. I think you'll get it no problem. Did you get C was 3? And the displacement, you get the constant to be 2. Now part C is asking, when is the particle at rest? So we have to interpret this at rest, meaning not moving. So if it's not moving, your velocity is 0. So we go to our velocity equation, and we can plug in 0 for velocity, and this factors nicely, and we find the 2 times that it is not moving in an instantaneous moment. It's like throwing something up in the air. It'll eventually change directions and come back down, and apparently it's at rest at the very top. If you threw me up in the air, the very top, I probably wouldn't be taking a nap. I'd be scared. But at rest just means that its velocity is equal to 0. And then now that we've found those times, if we want to find the displacement at those times, we could plug those values into your displacement formula. So sometimes the tricky part about kinematics questions is you always have 3 equations. You have a velocity equation, an acceleration equation, and a displacement equation. And you have to interpret the question to know which equation should I be using in this situation? What is this question talking about? So I'm plugging my numbers into the right formulas to get the right values. Is that good? Is everybody done? Okay. Now we're going to talk about the difference between displacement and distance. And this, I realized for myself, this is why I have trouble going for a run. I know it's good exercise. But if I leave the front of my house and I go for a run, in a certain amount of time, I'm going to get back to the front of my house. And my brain says, it would have been a lot easier if you just would have stayed there and not done the run. So in the run, I've traveled a certain distance, but displacement-wise, I'm back to the same place. So I feel like I haven't accomplished anything. I know I should feel like the exercise was good for me, and that'll, that should help me with playing soccer and all those things, but the rest of me goes, you got back to the same place. However, if I needed to get from point A to point B, and I needed to go there, then I could run, especially if I was late. Because I'm like, now I have a purpose from getting, and my distance and displacement might be the same thing. So, if displacement and distance, if we think of them as integrals, areas under the curve of velocity. So if we find the area under a rate of change, that shows us an accumulation of change of what's happening. If I run and return to the same place, I would probably have some area that was positive and some area that was negative, because I would be getting farther away from my house and then getting closer back to my house. They cancel each other out and I get 0. If I want to find the distance, I need to find my x-intercepts of when I'm changing direction and find my area of one and the area of the other one. If you have your calculator, making your velocity equation an absolute value inside would make all of your areas positive. And then you would get your distance. Okay? So a negative displacement is a positive distance. So if you have a rate of change graph, the area under that curve is your accumulation of change or your displacement. This shows that your displacement, you're getting farther away from your house. Then this negative displacement would mean you're getting back closer. And then you run farther away again from your house. If we want to know the distance this person has traveled, each of these three areas would have to be positive. But your displacement would consider this second area as negative. So it's important to realize the difference between, and anytime you just do a regular integral, it's like a displacement. It's finding the overall change, both positive and negative. But any time that you want to find your distance, you have to think of all of them positive. It's like, what is the actual area between the curve and the x-axis? So here we have a velocity equation involving sine. And we want to find the object's displacement over the first 3 pi over 4 seconds. Trying to think, what real life example would you ever use pi when referring to time? Have you ever asked your parents or siblings, what did you do in the last 5 pi minutes? Integration of this is pretty easy. We have a chain rule here, right? If you did the derivative of sine 2t, you would multiply by 2. So integrating, we have to think about taking away that chain rule. So we would divide by 2. Also, if the derivative of cos is negative sine, does it make sense that the integral of negative sine will be positive cos? So I generally was sine and cos because that negative and positive just got worse when we added integration. When you had just derivatives, you were like, okay, derivative of sine was positive cos, derivative of cos was negative sine. But now when you're working backwards, the integral of positive sine, oh no, that's negative cos, and the integral of positive cos just stays positive sine. Your positive and negatives can get all mixed up. Me personally, I remember one well with derivatives. Like if I remember well that the derivative of cos is negative sine, then I always use that as a starting point when I'm double checking and working backwards. And now we can plug in 3 pi over 4 and 0. And we get 3 pi over 4 minus 1, which is approximately 1.36. In part B, now it's asking for the distance. If we look at a picture of our graph, In our displacement, it didn't matter that some was positive and some was negative. Your calculations took that into consideration. It subtracted that red part and added the blue and the purple parts. And we got that 1.36. If we were finding out where these 2 points are, pi over 12 and 5 pi over 12, you would have to, if this was non-calculator, you would have to solve this equation. Find out where your x-intercepts are. Sine 2t equals 1/2. So it's a bit of, I would call this in my class, I call it a multi-revolution question. What you do is you solve for 2t, just like this was a theta, and say, I know from my unit circle that that happens at pi over 6 and 5 pi over 6. In fact, it keeps on going. There would be an infinite amount of solutions that we could find. But since I'm looking at the graph starting at 0, I'm really only interested in the first solutions. But just so that I can write, I'm going to write one more down. Would you agree that the next one, coterminal with pi over 6, would be 13 pi over 6? And it would keep on going. And then when you want to solve for t, you have to divide by 2 or multiply by half. If you kept on going, this would be 13 pi over 12. But we're only looking in the first 3 pi over 4 seconds. 3 pi over 4. Oops. Careful. Is 9 pi over 12. Can you see that this 13 pi over 12 isn't in that range? I just want you to be careful because sometimes students just do 2 and stop because they're like, you're so used to just going once around your unit circle. Sometimes the ones that keep on going do become part of your solution. So we could figure out pi over 12 and 5 pi over 12. And this is what you'd have to set up as your integral. If it was non-calculator, you would have to evaluate each of those without a calculator. If this was a calculator question, I would take our original equation. So the quickest way to solve this one would be to go from 0 to 3 pi over 4 and then put your original equation, which was 1 minus 2 sine squared theta, in absolute values. 1 minus 2 sine 2t. If you had a calculator, that's what I would do. That would flip that little part up, and then it would calculate all your areas as positive. If you didn't have a calculator, all of these answers would have pi's in them. And plugging in 5 pi over 12 with that 2 in the equation, they actually are all values on your pi plate. So it is doable to get this as an exact answer. Yes. How far? That's good. Is this good? Yeah. So for your physics AP, did you do that last year and are done? Okay. There's no physics AP this year. You just get a break from physics then this year? Sort of? Okay. Now, in physics, do you get a formula sheet for your exam, or do you have to have all your formulas memorized? You get a formula sheet. You get a formula sheet. as opposed to calculus where they give you no formulas. Right. So for those of you that have taken physics, just check. Are we all good? Almost? Yes? Okay. For those of you that have taken physics, you could solve this equation with the formulas that you know. If you have your formula sheet, or else maybe some of these you've memorized. But a golf ball is thrown up with a velocity of 7 meters per second from the edge of a cliff 75 meters high. How long will it take the golf ball to hit the ground at the bottom of the cliff? So you have a bunch of physics formulas that you'd be like, oh, based on what I know, I plug things in, solve for other stuff, and I figure it out. What we're going to do now is we're going to think of this from a calculus perspective. So there's a cliff, golf ball's thrown up in the air, and lands later on. Okay. What do we know? There's gravity involved. And gravity is constant. So you know your acceleration is a constant number of negative 9.8 meters per second. And if we know our acceleration, we can stop and work backwards. So if that's my acceleration, and I know that at time 0, my velocity, my initial velocity is 7, I also know at time 0, my initial displacement is 75. If I integrate my wonderful equation for gravity, I get a velocity equation with a plus c. This time I went with C1. Kind of foreboding that there will probably be a C2 in this question. And since we know our initial velocity is 7, you can plug in 0 for t and 7 for v. And c has to be 7. So our velocity equation, I'll just put a v here, is equal to negative 9.8 t plus 7. Does it make sense to you that your C1 value will always be the initial velocity? Because when you plug in t for 0, the 9.8 will always go away. And so that'll always become our initial velocity. Now, if we integrate this, we're going to get our displacement, which is going to give us a negative 4.9 t squared, a plus 7t, and then a c2, and if we plug in 0 for t, it should make sense that your c2 is your initial height. And the question, now that we have all of this information, was, how long will it take the golf ball to hit the ground at the bottom of the cliff? How long says I should be solving for t? When it hits the bottom of the cliff, what is it telling us? Is it telling us a displacement, a velocity, or an acceleration? It's telling us a displacement. So I go to my displacement formula, and I can plug in 0 for s. And now I just have to solve this equation. This is looking kind of unfactorable with the 4.9. Doesn't it feel a little bit unfactorable? That's the problem. Who invented gravity? They could have given us a nice number that could factor easily. You know what they do in grade 11 math? They round it to -5 Does anybody know their gravity in feet per second? Negative 32. So you'll often see in American textbooks they have negative 16. Canadian textbooks they have negative 5 because we're using meters per second. And they're both rounding a little bit to make it nicer. But yeah, this doesn't factor, but if you did solve it with quadratic formula, or I would probably use my graphing calculator in this situation, you get two answers because it's quadratic. Why do I have an x through the negative 3.26? Negative time, like I'm going to throw a golf ball off a cliff, and about 3 seconds before I throw it, it's going to hit the bottom. Right? We have to take into consideration the question. Only the positive answer makes sense. No formulas needed whatsoever. Just integration and our initial conditions, and we can create all the equations that we like. This is one using gravity. Okay? So it is still required that you know gravity. But it often feels in these questions that at first you feel like you don't have quite enough information. So we look at this question here. Nathan's designing a car, doing some research. I don't know, if you increase your speed steadily, maybe that's the best for fuel consumption, right? And maybe if you have some fancy car, now you'd probably go electric because that would save you even more on gas. But maybe if you had something built into your car that you get better fuel efficiency than somebody else, right? You step on your gas, but it doesn't really listen to you. It does a computerized proper acceleration to use less gas to save you money over time. And if one car company can be more efficient than another car company, that might be just the edge in the market they need to sell their vehicles over another. So Nathan here is designing a car that would increase its speed steadily until it reaches 100 kilometers per hour. Maybe this is really good for fuel consumption. So one day, he sets out on the highway and reaches 100 kilometers per hour 20 seconds later. How far did he go in those 20 seconds? Okay? I remember the first time I read this question, it was sort of like, I feel like I don't have enough information. Seems like it's very sparse. But how do we use our information? What? Got a nice Greek letter. Does anybody know what this Greek letter is? Lambda. I don't know. Just wanted to have a little fun. My acceleration is constant. So you could have used K. You could have used any letter. I went with the Greek letter just to have some fun. It's constant, but I don't know what it is. Could be 5. Could be 12. I'm not sure. What are we doing? Kilometers, meters per second. Okay? We have different units here. So we also have to make sure we're dealing only in one unit. If I want meters, my 100 kilometers per hour needs to be changed to meters per hour, but I don't want hours, I want seconds. So every hour has 60 minutes, and every minute has 60 seconds, so every hour has 3,600 seconds. So first thing I did was I took my 100 kilometers per hour and I converted it to 27.7 meters per second. How much fun and how messed up would the world be if they all of a sudden decided to change all traffic signs from kilometers per hour to meters per second and change your speedometers and everything, you think people would be messed up for a while? Some forever? Probably. Also, our velocity, let's change those to units, okay? I'll leave you to do the 100, I'll do the 0. 0 kilometers per hour as a velocity changes nicely to 0 meters per second. If you do the same math of changing the kilometers to meters and divide by 3,600, your 100 kilometers per hour changes to 250 over 9 meters per second, which we already have as a decimal there. When we have an initial velocity, we're starting off at 0, and we're getting up to 250 over 9 meters per second. Oops. So what do we have? We know our velocity is going to be the integral of acceleration. And even though we don't know what our acceleration is, it's some constant. It's some number. I chose lambda. So can I integrate any number? Yes. I would just have, if I use t as my variable, lambda t plus c1. Can I figure out what c1 is? Yes. Because I know my initial velocity was 0. So if I plug that in, I can figure out that c1 has to be 0. I also know that after 20 seconds, my velocity is 250 over 9, and now I have something set up. I can actually calculate the acceleration this vehicle is doing. 25 over 18 meters per second squared. And that allows me to write my velocity equation with just numbers. We wanted to know how far the car traveled in 20 seconds. That's a displacement kind of question. So now we have to work with our velocity equation to find our displacement. Pretty easy integral plus c2. We know that initially at time 0 our displacement was 0. So c2 would equal 0. And now we can just plug in what's going to happen after 20 seconds. $277.8 meters. Is that crazy fast or not crazy fast? I kind of feel not too crazy fast, okay? Because I think of the 100-meter Olympics, 100 meters. What do those super fast guys run the 100 meters in? 10 seconds around? This goes 300 meters in 20 seconds. It's faster. Yes, it's going faster than people can run. But I generally feel cars are able to do that. So I don't think of this as too insane of a situation. Interesting thing in this question is we knew acceleration was constant, but we didn't know what it was. So we just started with some variable, not a variable, some letter to represent that constant, and worked with it, and we found out that through our integration, hey, I have enough information I could actually solve for it. and then work further. So initially when you read this question, you probably felt there wasn't enough information because the acceleration wasn't given, but there was enough things to plug things in and solve as we go. And we did all of this without any physics formulas, just using calculus. Do I need to scroll up? Are we good? Awesome. Okay. Now, in last class, we talked about average of a function. So the word average can sometimes throw you off because sometimes you can just use the slope of the secant line, and sometimes you should use the average of a function formula. So someone is asking for average velocity. And I traveled 100 kilometers in 1 hour. My average velocity is 100 kilometers per hour. That doesn't mean I traveled exactly that speed the whole time. But my total displacement over my total time will always give me my average velocity. I could also find my average velocity by taking my velocity formula, integrating from A to B, and dividing by 1 over B minus A. That was our new formula that we learned for average of a function the other day. Careful, there's a difference between average velocity and average speed. Okay? Because velocity takes direction into account. And average speed just takes how fast you're going. Right? If I go 100 kilometers an hour in this direction, 100 kilometers back to where I started, my average speed is 100 kilometers per hour. But my average velocity would be 0 because I'm right back to where I started. So here we have the absolute value bars inside because we would be like a distance formula. We need the total distance traveled. And average acceleration, you could take your velocity formula and basically find the secant line or the slope. What was your velocity to begin with? What was your velocity to end with? How much time did that take? That's going to be your average acceleration. Or you could take your acceleration formula and solve that as well. So we've got a velocity, and this particle is moving just along the x-axis. In which direction is it moving at t equals 5? Well, if we plug in t equals 5, we get a velocity that is positive. Positive will mean it's moving to the right. A negative velocity would mean that it's moving to the left. Find the acceleration at time t. Well, just find your derivative to get your acceleration formula and plug in 5. No problem. So we define a function x of t. I like the variables here because your particle's on the x-axis. So x of t is basically its position somewhere along the x-axis at time t. And we know at time 0, it starts at position 12. So it's starting 12 units to the right. We want to find out where it is 3 seconds later. Well, x of t will be its displacement. So its position would be the integral of our velocity. Oops, wow. And if I look at the area under the curve from 0 to 3 of my velocity graph, that will tell me how much change has happened. We know that x of 0 is 12. Now there's the actual equation. So if I plug in that actual equation and find its integral and plug in 0 and 3, what this tells me right here, this negative 16.5, is how much it's changed from 0 to 3. Is there the letters you can't read? Yeah, which ones? In here? On this side?
Yeah, like I see it.
This is x of t.
X of t?
Yeah.
Thank you.
So when I find the integral from 0 to 3 of the actual equation, this is like the area under the curve from 0 to 3. That area under the curve is an accumulation of change. From 0 to 3, our displacement changes minus 16.5. It's going to go back minus 16.5 from wherever it started from. If we think about where it started from 12. If I started at 12 and went back negative 16.5, does it make sense that at 3 seconds I would be at negative 4.5? So that's one way of looking at it. The other way is just using the fundamental theorem of calculus part 2, right? If I integrate this, I'm going to get displacement from 0 to 3. Fundamental theorem of calculus says plug in 3, plug in 0. And this has to equal negative 16.5 because we've actually done that method. Well, if I want to find x of 3, and I know that x of 0 is negative 12, and I end with negative 16.5, I could just rearrange that equation to get negative 4.5. But overall, as far as a thinking process goes, what's going to be the most helpful is for you to realize that when you integrate a rate of change, it's going to show you an accumulation of change. So from time 0 to time 3, we have an accumulation of a minus 16.5 of change. Meaning wherever you started, you have to go back minus 16.5. The question told us you started at 12. That means 3 seconds later, you're going to go back minus 16.5. You're going to end at minus 4.5. Find the distance traveled of the particle from 0 to 6. Yes. No, you. I'll start again.
If we do the second method.
No, this is all. I mean, you still need in method 1 here. You still need this to get this number, right?
If we choose to work like that, though, we won't be adding plus c to our formula.
No, because anytime you do the plus c is when you just do an integral with no numbers. As soon as we have numbers there, the definite integral, the plus c goes away.
If you took the indefinite integral and then did the plus c, could you just also do like, oh, t is equal to 0 and then find what c is?
So find the total distance traveled from 0 to 6. Total distance traveled would be the absolute value, so if we had a calculator, we would definitely do it this way. We draw a picture of that. We have part of it being negative, you would have to have it flipped up. If this was non-calculator, you would have to find this x-intercept of 4. And do the integral from 0 to 4, make it positive, and then do the integral from 4 to 6. One of the ways that you can make the integral from 0 to 4 positive is just throw a negative out in front of it. That's perfectly fine. Or you could have just added absolute value bars around that. Any of those notations would be fine. They indicate that you know that that answer is going to be negative. We need to make it positive to find the total distance. And you'll just have to trust me, we did the math right, to get 94 over 3. Part E. Notice it says average speed. If it was average velocity, you would do change in displacement over change in time. Average speed is change in distance over change in time. So since we already figured out that the distance traveled was 94 over 3 and the change in time is 6, we'll get 47 over 9. And finally, the last question. For what values of t is the particle's instantaneous velocity the same as its average velocity? So if I want to find average velocity, I could use my average function formula, or I could do my change in displacement over change in time. It happens to be a nice minus 1. Instantaneous velocity, we want to actually set our velocity formula equal to -1 and solve for this. You have to either use the quadratic formula here or your calculator, because it does not factor nicely. And since one of the times is negative, we only choose the time that is positive in the end. So instantaneous velocity, that's an actual time when the velocity is that.